Welcome to this episode. I'm going to look at the chapter 16 of this special publication of SEG. It's about studying sulfide melt inclusions in a magmatic arc, which is called Kohistan arc, located in Pakistan. This study is quite fascinating. It explores how Chalcophile metals, including copper, gold, and PGE, behave deep in our crust, using lower crustal accumulates from the Chilas Complex in the Kohistan arc of Pakistan. The researchers in this study worked with 30 accumulate samples. They're mostly gabbros and handful of dunites. They applied a range of geochemical techniques, ICPES, ICP-MS, and the real breakthrough came from laser ablation ICP-MS analysis of tiny sulfide inclusions, which are trapped in minerals like olivine, pyroxene, and amphibole. And those are like time capsules of early magmatic processes. They also measured osmium isotopes by isotope dilution, which helps distinguish mantle versus crustal contributions. And what they found was quite surprising. Sulfide phases were scarce, with less than 0.2% by weight. They were extremely metal rich. Copper contents reached up to 34 weight%, while gold and palladium were carried in moderate but significant amounts. Two main sulfide types appeared in these samples and studied in this study, which include monosulfide solid solutions, or MSS, which are more nickel and iron rich, and copper rich intermediate solid solutions, or ISS, which also hosts trace metals like palladium and gold. When they modeled metal loss due to sulfide segregation in the lower crust, the results were striking. More than 95% of palladium and platinum, between 33 to 85% of gold, and even 30 to 60% of copper could be stripped from the melt before it ever reached shallower depths and levels. And what this tells us is that the metal budget of porphyry systems is largely determined in the lower crust. By the time magmas ascend, they were already depleted in PGEs and gold, yet they still carry enough copper to generate porphyry copper deposits. And this challenges the idea that porphyry systems need a second stage of sulfide remobilization in the upper crust. Instead, the Chilas Complex points to a single-stage porphyry model where deep crustal filtering does the heavy lifting. In short, the Chilas Complex offers rare lower crustal evidence that explains a long-standing puzzle why some porphyry copper deposits are rich in copper but consistently poor in gold and PGEs. Let's zoom out and take in the bigger picture of the study area. What you're looking at here is a Kohistan paleo arc, and it's one of the best preserved arc sections anywhere in the world, sitting right between the Indian plates to the south and the Karakoram plate to the north. And this is a simplified geologic map adapted from Jagoutzs and colleagues in 2006. It shows the entire crustal architecture of the arc, from the volcanic rocks up top, down through the metasedimentary packages and all the way into the ultramafic roots. Kohistan preserves what is essentially a slice of ancient oceanic crust and mantle frozen in place. Now the orange body in the center is the Chilas Complex, or the study area of this research. And it's a real star of today's story. It's a massive lower crustal cumulate dominated by gabbros and dunites. And this is where we start to see how chalcophile elements are partitioned and trapped during arc magmatism. The red stars here mark sample localities and stretch across the arc, and they're crucial because they let us track the evolution of metals as we move from deep-seated cumulates all the way up toward the volcanic carapace. And if you look closely, the green bodies at Jingao, Sapat, and Toratiga, they are places preserve the mantle signature, recording the very first stages of magma generation. The entire system formed during the Cretaceous, when the Indian plate was being subducted beneath Eurasia. Later, during continental collision, this arc was welded into place, giving us a near continuous record of processes that usually remain hidden deep beneath active arcs today. So this map is not just a colorful sketch, it's a roadmap to one of the Earth's most extraordinary natural laboratories. It's a place where we can trace the journey of metals from the mantle through the lower crust and ultimately to the zones where our deposits form. Here in these pictures we see tiny plebs, which are trapped droplets of molten sulfide, and there are actually little time capsules frozen inside early crystallizing minerals. Minerals like olivine, amphibole, and even pyroxene in the Chilas Complex. Let's begin with images A and B. These images show beautifully preserved inclusions in olivine and amphibole, where immiscible sulfide melts crystallized into pyrrhotite, pentlandite, and chalcopyrite. The droplets are rounded, almost perfectly spherical, which tells us they were once molten before being sealed inside their host crystals. And they're not just random grains, they're physical snapshots of a magmatic process that happened in real time as the crystals grew. Image C, though, is one that really stands out. Here we see a chalcophile, a chalcopyrite inclusion, but inside it, it's something extraordinary. We have electrum, which is natural gold and silver alloy, and it's clearly visible in this EM. It's quite rare to find precious metal alloys preserved like this. The fact that electrum exists within a sulfide droplet shows that the gold wasn't just dissolved in the system. It actually separated out to form its own alloy within this microscale sulfide pockets. And that's a remarkable clue about how gold behaves in arc magmas, and it underscores the intimate connection between base metals and precious metals during magma differentiation. Then we move to images D and E, which show a different style together. These inclusions are fully enclosed within olivine and amphibole, unexposed, completely sealed off from the outside world since they crystallized roughly about 85 million years ago. They are pristine, untouched by alteration, weathering, or diffusion. And for geochemists, these inclusions are priceless because they preserve the original chemistry of the trapped sulfide melt. And they are the closest thing we have to opening a time capsule from the lower crust. What makes this dataset so unusual is not simply that sulfide inclusions exist, you can find them in other deposits and other geologic settings, but the extraordinary fidelity of the preservation, the presence of precious metal alloys like electrum, and the fact that all of these comes from a lower crustal accumulate. It's an environment where sulfide saturation isn't typically expected without crustal contamination. Together, these inclusions provide rare, direct evidence that even small amounts of sulfide in the lower crust can capture copper, gold, and PGEs, stripping them from the magma long before it reaches the upper crust. And that reshapes how we think about the deep controls on metal budgets in arc magmatic systems. Now we shift from imagery to data. And what you're seeing here are time-resolved spectra collected as a laser ablates through tiny sulfide inclusions hosted in minerals like olivine, pyroxene, and amphibole. Each sharp rise or fall in these curves tells us exactly when the laser beam intersected the sulfide pocket and what elements were locked inside it. Take panels A and B first. They both show copper-rich inclusions, one hosted in olivine and the other in amphibole, around 36 to 38 seconds. That's the moment the laser hit the sulfide droplet. But notice what else happens. Gold, palladium, and even silver spike at the same time. And that's direct evidence that these trace metals were tightly bound inside the sulfide phase. They're not hanging around in the silicate host. In panel C, the spectrum comes from monosulfide solid solution or MSS type inclusion in pyroxene. And what stands out in this panel is a dual spike in nickel and copper, suggesting that the sulfide itself is zoned and likely recording a transition between MSS and ISS domains. This is the kind of fine-scale partitioning you would only catch with laser ablation data, and it's rare to see it preserved so clearly in a natural system. Then look at panel D, another amphibole hosted inclusion. Here the behavior of the PGEs looks scattered and irregular, but that's not a random noise, that's the nugget effect. That's the signal that these metals are probably hosted as nanoparticles or microalloys, even electrum, rather than being evenly distributed within the sulfide lattice and the structure. So what's unusual about this dataset? It's the level of detail. We are not just identifying which elements are present, We are watching in real time how metals like gold and palladium partition as a sulfide melt crystallizes deep in the crust. These inclusions capture the dynamics of sulfide saturation at sub-second resolution, and that's critical because it shows us how early sulfide phases can strip copper, gold, and PGEs from magmas long before they ever have a chance to rise and form porphyry deposits at shallower depths. Let's step back here and look at the bigger picture. How do the deep cumulates of the Chilas Complex compare to magmas that eventually form porphyry copper systems? Panel A lays the foundation. This plot shows whole rock metal contents normalized to the primitive upper mantle. Most gabbros sit low in gold, PGE, and as you would expect, but one sample, a dunite which is called K6, breaks the trend completely. It's off the chart, enriched by orders of magnitude in copper, palladium, and gold. And the reason? It hosts visible sulfides. This rock is essentially a hotspot of sulfide accumulation and possibly even a localized mineralized zone frozen into the lower crust. Now, the panel B, we have iron, sulfur, and copper ternary diagram. Here, sulfide inclusions plot between the MSS and sulfide liquid fields. What makes this diagram unusual is a trend pushing toward ISS type copper-rich compositions, and that's a signal of partial melting and sulfide fractionation happening in the lower crust. And that's something rarely documented in porphyry literature, where most models emphasize shallow level processes. And panel C is where it gets really striking. The copper-rich inclusions, especially the ISS types, are absolutely loaded with palladium, platinum, and gold, up to thousands of times mantle levels and values. This tells us that even tiny sulfide droplets are incredibly efficient at scavenging chalcophile and siderophile metals. In contrast, the MSS type inclusions, they lean toward nickel and cobalt, showing internal zoning and chemical evolution as the sulfide melt cooled. And this kind of high resolution fingerprint with PGEs so strongly partitioned is rarely preserved and offers a unique window into the deep magmatic filter. Finally, panel D pulls it all together. These are modeled parental and derivative melt compositions compared against natural arc lavas from Granada and Paul Ridge. And the story is clear. The parental magmas of Chilas Complex started with decent amounts of copper, gold, and palladium, but after interacting with just a small volume of sulfide, modeled with melt to sulfide ratios of 1000 to 10,000, the derivative melt that ascends toward the upper crust loses more than 95% of its PGE, most of its gold, and a large share of its copper. But even after this deep filtering, the melt still carries about 50 ppm copper, which is more than enough to generate porphyry copper deposits. What is unusual here is that this massive metal depletion takes place entirely in the deep crust. It doesn't require a second stage of remobilization or fluid saturation at shallow levels, which is the backbone of many Andean style porphyry models. Instead, the lower crust itself acts as a powerful metal filter, stripping magmas of their PGEs and gold long before they reach levels where ore deposits form. And this figure is one of the clearest demonstrations of how powerful the sulfide filter can be in deep arc crust. What you're looking at here are depletion factors, essentially how much of each chalcophile element remains in the magma after a small amount of sulfide melt segregates. The three curves represent slightly different amounts of sulfide segregation: 0.1, 0.12, and 0.17 weight percent. That is less than a fraction of a percent, yet the effect is dramatic. And watch what happens to the platinum group elements, especially platinum, palladium, and they collapse almost completely with more than 99.9% removed even at the lowest sulfide level, because these partition coefficients into sulfide are so astronomically high that even the tiniest droplets acts like a magnet. Gold also takes a major hit, between 80 to 95% removed, depending on sulfide dependent abundance. But copper behaves differently. Its depletion is relatively modest, and that's critical because it means that even after this deep filtration, the magma still carries enough copper to form porphyry deposits higher in the crust. Now look at the silver and bismuth. They stand out because they don't follow copper as closely as you might expect. Instead, they remain relatively mobile, hinting at different partitioning behavior in deep crustal conditions compared to shallow systems. And here's the takeaway. All of these effects, the loss of nearly all the PGEs, most of the gold, and part of the copper budget, are caused by less than 0.2% sulfide melt. You wouldn't even notice that the amount in a hand sample, but chemically it's devastating. And that explains the paradox. A parental magma may start out loaded with PGEs and gold, but by the time it rises into the upper crust, it's already being stripped bare, carrying copper forward but leaving the rest behind. In short, this diagram shows the sulfide filter at work. A microscopic volume of sulfide melt in the lower crust has the power to predetermine the metal potential of an entire arc system. As we wrap up, let's return to the central message of this study. What the Chilas Complex reveals is that even tiny amounts of sulfide melt, less than 0.2% by weight, can completely reshape the chemistry of arc magmas. These sulfides behave like metal sponges, pulling gold, palladium, and platinum out of the melt with extreme efficiency, long before the magma ever has a chance to rise and form a porphyry system. This process, deep crustal sulfide segregation, strips out most of the precious metals, but it leaves copper relatively mobile. And that's why so many porphyry systems we see at the surface are copper-rich but poor in gold and PGEs. And evidence comes from sulfide inclusions preserved in early minerals like olivine, amphibole, and pyroxene. And these inclusions are essentially time capsules, capturing the exact moment when metals were partitioned away in the lower crust. It's a glimpse into processes we rarely get to see so clearly in other magmatic arc settings. And the modeling is equally striking. Our factor calculations show that over 95% of PGEs and more than 80% of gold can be stripped out by deep sulfides. And this supports a single-stage porphyry model, one where the lower crust itself dictates the ore potential without needing a late-stage remineralization step near the surface. So the big takeaway is this. The fate of a porphyry deposit may be sealed deep in the arc crust, long before any voids or shallow processes ever came into play. Thanks for watching.